Hello, my name is Jacob Marks. I worked with Brandon Montano, Jiwan Chong, Manjusha Raavi, Raisa Tomas Cerny, and Dongwan Shin on differential privacy applied to smart meters, a mapping study. So, in this systematic mapping study, we analyzed 55 papers on differential privacy applied to the smart grid. We provided a broad overview of the research and found what common data sets and noise methods researchers used. We also found some of the most common intentions for future research, the balance between privacy and utility, and how to cope with attacks and still protect user privacy. Now, in this talk, first I'm going to introduce the topic and goals covered in our paper. I will then discuss the background, what is the smart grid, and how is the privacy of its users protected. I will discuss our methods for the systematic mapping study. I will discuss our results and the conclusions we've reached from those results. First off, what is the smart grid? Well, the smart grid is a planned and partially implemented utility infrastructure. It will allow electric companies to monitor and optimize the power grid. It will do this because it collects much more fine-grained electricity usage data than older electrical meters. This fine-grained data could also be used by customers to help understand their electricity usage patterns, or it could be used by researchers. However, with these advantages also come some serious privacy concerns. With this fine-grained data, it might be possible for someone to identify the number of people living in a house. They might be able to find out somebody's economic status, when they're at home, what appliances they're using, and what time they're using them. And even with fine-grained enough data, it can be possible to detect what you're watching on TV, according to Baylor et al. In multimedia content identification through smart meter power usage profiles. So obviously, there needs to be rigorous methods to protect the privacy of smart meter users. Two major privacy concepts that have been applied to the smart grid are cryptographic privacy and statistical privacy. With cryptographic privacy, the smart meter is sending its data to a valid receiver, the utility company, and we want to prevent anyone from intercepting the data. This is a very different concept from statistical privacy. With statistical privacy, the attacker is not particularly different from a legitimate receiver. The goal of statistical privacy is to prevent any information harmful to an individual in a database from being discovered. Differential privacy, the major topic of this paper, is an especially promising statistical privacy definition. In The Algorithmic Foundations of Differential Privacy, Cynthia DeWerk and Aaron Ross describe differential privacy as a promise that you will not be affected, adversely or otherwise, by allowing your data to be used in any study or analysis, no matter what other studies, data sets, or information sources are available. Basically, it should be very unlikely that an attacker could identify whether or not you are in a data set. This gives you plausible deniability and privacy. The formal definition of differential privacy says that a mechanism A is differentially private if the probability of A applied to database B, if the probability of A applied to database 1 being in S is less than or equal to e to the epsilon times the probability of the mechanism A being applied to database 2 also being in S. This is where the two databases differ only by one element. And the important value to note here is epsilon. So epsilon is the privacy parameter or privacy budget for differential privacy. It defines how private the system is. An epsilon value of 0 will mean complete privacy, while higher values guarantee less privacy. According to the authors of DREAM, Differentially Private Smart Metering, the modification of any single user's data in the dataset changes the probability of any output only up to a multiplicative factor of e to the epsilon. So this gives us a way of measuring the privacy of a mechanism. But what do we use for the mechanism? To preserve differential privacy, the mechanism must take the value of epsilon into account. The mechanism then adds different amounts of noise depending on how much privacy is required. One of the most common mechanisms used in examples and in the majority of the papers we analyzed is the Laplacian mechanism. The more noise that is added from the Laplacian distribution, the better the privacy. However, your data also becomes less useful. This balance between data utility and data privacy is one of the most challenging aspects of implementing differential privacy. One, the noise is added to the data must be aggregated in some way. Just adding noise to the data is not enough to ensure differential privacy is maintained. Going back to cryptographic approaches for privacy. The goal is fundamentally different, however, it is complementary, not opposing. Differential privacy cannot be guaranteed if a user's data is compromised before noise is added, or before the noisy data is aggregated. This complementary nature is quite evident in our mapping study because 25 of the 55 papers used some type of cryptographic method. Some of the common cryptographic methods applied to smart meters are homomorphic encryption, which allows encrypted values to be aggregated before they are unencrypted, and symmetric and asymmetric DC nets. So that's our background. But our goal for this paper was to better understand the current research applying differential privacy to the smart grid, and to better understand what topics researchers are most interested in exploring in the future. A systematic mapping study seemed like a good way to accomplish this. The goal of a mapping study is to describe the kinds of research activity that have been undertaken relating to a specific research question, according to Brereton et al. Diane Cooper states that mapping studies are based on the concept that published articles not only represent findings, but indirectly represent activity related to the finding. So what are people researching? What are they referencing? What do they connect that to? The first steps for our mapping study was coming up with 4 research questions. These research questions represent topics we hoped would inform us more about the current and future state of the research. Our question 1 is, what are differential privacy preserving methods, tools, strategies, and techniques applied to smart meters? And what is their distribution in the literature? Our question 2 is, what subjects or topics have been addressed in the research for differential privacy in the smart grid, and what is their distribution in the literature? Questions 3, what datasets are used to study differential privacy applied to smart meters? Question 4, what is the future direction in the research of applying differential privacy to smart meters? Now, using these questions, we needed a way to search for research papers systematically. We needed papers that would answer these questions specifically. So what we did was we pulled keywords out of our questions and searched for these in the body of our text. So we searched for data, attack, threat, identification, security, user control, third party, and battery. Some of these as the full 2 words, user control, and some of these we wouldn't worry about whether there were more letters connected after data. Now, in order to make sure the papers were truly focused on differential privacy in the smart grid, we required finding these words within the abstract of the papers. We hoped that this would ensure that differential privacy or the smart grid wasn't just brought up as a side note in the background, for example. Now, we used this search string in IEEE Explorer, ACM Digital Library, and the Elsevier Science Direct search engines. In addition, we also used the sources referenced in Differential Privacy Techniques for Cyber-Physical Systems, a survey. This is a very recent survey from 2019, and we hoped it could add a few additional sources. It was also a survey we were more familiar with, so we hoped this would better ensure that our research was accurate. Now, so this was the search string we used and the search engines we used it in. But in order to make sure the sources we found were valid, we had inclusion and exclusion criteria. An article would pass our inclusion criteria if it relates to differential privacy and the smart grid. However, we would exclude an article if we could not gain access to the article, if it was a repeated result from another search engine, or if we could not read the paper. Now, once we had our papers, we needed a clear method for answering our original questions. To do this, we created simpler categorical and yes or no questions that we could answer. So we categorized the noise methods used, and the rest were true and false for research question 1. They were, was a variation on differential privacy used, not just regular differential privacy? Were different cryptographic techniques implemented? Was a performance evaluation done? Did this method use a trusted aggregator? Did it use an untrusted aggregator? And was a battery needed for this method? For research question 2, talking about subjects, we asked true or false questions. Was fault tolerance discussed? Was the scalability of the method discussed? Was monetary cost a subject? Were attacks on the system covered? Was user control over their privacy a point of discussion? Now for research question 3, this was already quite simple. It's just a categorical question. For research question 4, the future direction of the research, this was a little more complicated. What we did was we looked through the different discussions about future research for that topic, and we tried to put them into categories. If they didn't fit one of our existing categories, we'd put them in other. But we had user control as a topic for future research, attacks, the cost of the system, scalability, utility and privacy of the system, whether it could be applied to non-smart grid projects, whether they wanted to prototype or experiment with their project, and the performance of their method. So using our search string, we found 40 results from IEEE Explore, 3 results from ACM, and 7 from Elsevier. From the additional survey, we also got 12 papers that specifically discussed differential privacy applied to the smart grid. This came out to a total of 64 papers. After applying our exclusion and inclusion criteria, we had 55 papers. These papers were published between 2011 and 2020, with most of the papers having been written in the last 5 years. So that seems like a pretty good look at the modern state of research. Next, I'm going to talk about the results we found for each of our research questions, starting with research question 1. What are the differential privacy preserving methods, tools, strategies, techniques applied to smart meters, and what is their distribution in the literature? We found over 70% of the 55 papers had some form of performance evaluation. This is useful for knowing what methods will be preferential for real-world use. Knowing whether the aggregator, usually the utility company, is trusted is an extremely important topic. And sadly, 15 of the 55 papers did not clearly specify what trust model they were using. Of the ones that did specify, there was a nearly even split on the trust models used. 4 of our sources implemented both. We found 7 that implemented a differential privacy variation, 20 used cryptographic techniques, quite a lot, and only 7 discussed battery load hiding methods. I'll talk more about battery-based load hiding later. Now, still on the topic of methods, we categorized what types of noise methods were used in each paper. By far the most common was noise drawn from the Laplace distribution. This is not necessarily because it is the best distribution for the task, it may be used the most because of the high quantity of examples in other literature that implements it. Moving on to research question 2. What subjects or topics have been addressed in the research for differential privacy in the smart grid, and what is their distribution in the literature? By far the most commonly discussed topic is attacks. This is an extremely important subject when discussing privacy protection. As attacks will always be adapting, it is important that the research continues to have this focus. The cost is also commonly discussed. This is extremely important for actually implementing this in the real world. And it's also especially important when discussing battery load hiding methods. So battery load hiding methods are, they discharge a large rechargeable battery randomly to generate noise and hide the actual electricity usage. Now this works quite well for differential privacy. It's a good way to add noise without using a pseudo-random number generator often, and it can also directly hide the electricity data being sent to the utility company. The problem is these batteries can be quite expensive. A quarter of the papers covered fault tolerance, while very few covered user control. Now question 3 was quite easy to answer. What datasets are used to study differential privacy applied to smart meters? Now most papers would reference a dataset that only they referenced and no other papers referenced. Second most common was synthetic datasets instead of real-world data. But in terms of the repeated real-world datasets, the REDD dataset from MIT was by far the most common. Now for research question 4, what is the future direction in the research of applying differential privacy to smart meters? We categorized the various topics that authors stated would be important for future research. Attacks were listed by 6 papers, more than most of the other topics, but by far the most common was utility and privacy. This clearly shows the difficult balance between the two. Finding ways to accomplish the same level of privacy with better utility is the most important topic for future research. Because again, the problem is if you have a lower epsilon value, you're ensuring better privacy, but you're also adding so much noise to the data that the utility becomes much worse, and it may not honestly be usable in the smart grid. So finding methods that can accomplish the same levels of privacy with better utility is extremely important. Now beyond our research questions, we were curious if there were any correlations or connections between the various methods and subjects covered in these papers. Here in figure 5, you can see the correlations between all the methods and subjects. Now most of them aren't of any particular note, however there are a couple of interesting correlations. Trusted aggregator and untrusted aggregator are negatively correlated because they usually don't appear together. Cryptographic techniques are often used at the same time as trusted aggregator, probably because the aggregator is trusted enough to unencrypt the result. Cryptographic techniques are also discussed at the same time as fault tolerance, likely because cryptographic systems can have more issues when a part of the network is unexpectedly offline. Performance evaluation is often used at the same time as fault tolerance and also attacks. Also, when battery load hiding methods are used, the cost is extremely likely to be discussed at the same time, with a 0.37 correlation. Now, after seeing these correlations, I was curious if there might be a better way to illustrate the connection between certain methods and the subjects that are discussed because of them. In this table, you can see how much more likely a certain subject in the columns is when a certain method in the rows is used. Here it becomes especially apparent that if the battery method is used, if battery load hiding methods are used, then the likelihood that the paper discusses the cost goes up 48%. So if somebody was using a battery method, they were much more likely to discuss the cost. In the same way, if somebody used cryptographic techniques, much more likely to discuss fault tolerance. But if they used a differential privacy variation, they were much less likely. We calculated this by finding the total number where the method and the subject were both used, both true, talked about, and divided by the row true count, so exactly how many times the method was used. We then subtracted, this line here is an error, we then subtracted the total number where the subject was discussed divided by the complete number of papers. So this gave us, again, how much more likely a subject was to be discussed if a method was used. In conclusion, we performed a systematic mapping study to help us understand the current and future state of the research around using differential privacy for the smart grid. We analyzed 55 papers for the study. We provided a broad overview of the current research, finding common datasets used, noise methods, and other information about the subjects and methods used. We also tried to categorize the topics for future research that were most commonly brought up, finding that the balance between privacy and utility was by far the most common. attacks were also a large concern and will always need more research. Thank you for your time. Some of our most important references that I used in this talk are listed here. For the full list of papers referenced in our mapping study, please see the original paper. Thank you very much.